Welcome everyone to NSTA Web Seminars, where you can find live interactive learning at your desktop. Tonight's presentation is titled NGSS Core Ideas, Matter and Its Interactions. Our presenter is Joe Krajcik. We also have Ted Willard online with us to provide information about the development of NGSS. My name is Bryn Slate. I'll be moderating the program, and Jeff Lehman is online with us to provide technical support. Before we get started with the presentation, I wanted to remind everyone to visit the NSTA Learning Center, which is your online portal for Teacher PD, and we've got over 11,000 resources in the Learning Center. Over 3,800 of those are free. Everyone can add resources to their My Library area, so you can access those at your convenience. And the community forums are a great place to connect with other science teachers and discuss the ideas that are applicable to your classroom situation. If you need help finding things in the Learning Center, our online advisors are happy to help you out. We also have free tools that can help you manage your professional learning. It's all available at learningcenter.nsta.org. And I encourage everyone to take a few moments to check out everything that we have available in the Learning Center. Now I'd like to go ahead and introduce today's presenters. Ted Willard is our NGSS at NSTA Director, and he'll be providing some opening remarks for us about the development of the standards. And that'll be followed by our feature presentation with Joe Krajcik from Michigan State University. At this point, I will turn it over to Ted to get things started. Welcome, Ted.
Thanks, Bryn. Thanks, everyone, for being here. It's really great to start off the fall again, to start up another series here. We did a number of pieces last school year on the practices and cross-cutting concepts. I'll mention at some point later. I encourage you to go and look at that, but I'm thrilled that we're the first web seminar of the school year, and we'll get going here. A quick overview here to work with the Next Generation Science Standards. There was a work of 4 organizations: the National Academy of Sciences, the NSTA, the Achieve, and the American Association for the Advancement of Science. And this was basically a 2-step process to the standards. We started off with the development of the framework and then the standards themselves, and from these standards comes the work around moving the implementation to classroom with assessments, curriculum, instruction, and teacher professional development. Starting off with the framework itself to give a sense, the big point here of the framework is that these 3 dimensions: scientific and engineering practices, cross-cutting concepts, and disciplinary core ideas. If you have not yet read the framework, I would strongly encourage you to do so. There's no excuse, really. There's a free PDF you can get from the National Academy Press, or if you're someone who really likes a print copy, you can go to the NSTA Press store and order a copy and have it sent to you. The engineering practices, which I think are one of the most interesting pieces of the new standards, are really a description of tasks that students are expected to be able to do. Taskmaking doesn't really fully encompass it, but these things that students should be able to do as part of their process of learning about the disciplinary core ideas. And so asking questions or planning investigations. Some really important things here of developing models or constructing explanations and engaging in argument. All of these elements are central to what goes on with the standards. I'm sure Joe will talk about a little bit tonight. There also are cross-cutting concepts, these things that aren't indigenous to life science or earth science or physical science, but cut across all the different science topics. And so you can see the list of 7 cross-cutting concepts there. And then comes the disciplinary core ideas, what this series is going to be about. We're focused on the ideas in physical science tonight, particularly the first one, matter and its interactions. These pieces all break down into a further level of detail. So matter and its interactions has different sections that I'm sure Joe will talk about in a little bit. But as the same is true for all the other disciplines. So we go on to the actual standards themselves, and that was worked on. There was a group of 26 states engaged in developing the standards. They oversaw all the issues and all. The states in blue were part of that process in guiding the development. Any state now can actually adopt the standards. There's nothing that says the only lead states can. Anyone can. I'll talk about that in a second. Here's a showing of where the riders were sort of spread across the country, 41 some odd writers. Joe was one of those folks, and I do know we've got online tonight in attendance at least one other writer I noticed in the chat window. Here's a little quick set of talking about what the current state of adoption is. The states there in green have actually gone and adopted the standards. This now will be the situation in these states that students will, even though it hasn't been implemented in their classrooms yet, but eventually will be expected to know and be able to do what the standards in NGSS expect. And then the states in yellow here are engaged in some step in the process, whether it's been a polling state teachers by the Department of Education and getting feedback, or the board has begun discussion of a process in place on this. That's all taking place and moving along. So when we think about the standards, they're represented as performance expectations. That's what we have here. The statement, develop molecular models of reactants and products to support the explanation that atoms and therefore mass are conserved in a chemical reaction. And so that statement is what students should know at the end of instruction. It is not what they need to, it's what they to be assessed in doing. It's not instruction specifically to the teacher that this is what you have to do in the classroom. The teachers still have total freedom to plan out how to get their students to the point where they're able to do this performance expectation. But the performance expectation combines these three different areas. And so we have develop molecular models to support an explanation. That is a scientific and engineering practice. This idea of reactants and products and that atoms and mass are conserved, that's a chemical that's a disciplinary core idea as specified here in the orange box. And then we have this idea of conserving in a chemical reaction. That is a cross-cutting concept of that matter is conserved because atoms are conserved. And so this fuses all of those different elements together, and that's a real key piece of how the standards are set up. So with that in place, this is a little quick introduction and background. I want to turn things over to Joe, and looking forward to hearing what he has to say about matter and its interactions. Off to you.
Hi, everybody. It's good to see so many people online, and I want to both, as Ted and Breen did, welcome you to this webinar. And I also want to welcome you to the beginning of a new school year. That's why it's so nice to see so many people online, because I know it's the beginning of the school year, and I'm sure some of you are tired from being, you had a summer, and now we're back in full gear teaching. So welcome. So Breen, how do I move forward?
Arrows at the top.
So the arrows that you'll use are right above where my pointer is now.
So who am I? I'm a professor of science education at Michigan State University. I'm also the director of what's called Create for STEM here, which is an institute funded by MSU to improve the teaching and learning of math and science education K through 16. So that's what I do. Prior to going in higher education, I did teach high school chemistry for 8 years. And probably what's important for you to know related to this session is that I was both a member of the framework team. I was the head writer for the physical science standards, and I was also on the leadership team for NGSS. So what I'm going to do tonight, we're going to focus basically on one disciplinary idea. I'm going to actually talk a little bit about what is a disciplinary idea. And we're then going to talk about the relationship of core ideas to science and engineering practices. We'll speak a little bit about the NGSS and how these two, the framework and NGSS, are important. I will talk about the importance of building core ideas over time, particularly related to matter and its interactions, and some examples of the value of core ideas. So we, as Breen got you involved, we're also going to do a little poll here sort of to activate your prior knowledge related to our work. So here's our first little poll to sort of activate your prior knowledge. So what is the difference between a disciplinary core idea and a science concept? So please read the various options and select your choice.
Thanks, Joe, and I'll remind everyone how to respond to that poll. Joe, we've had a couple people say they're having trouble hearing you, so can you increase your microphone volume a little bit while we're working on this? I'll remind everybody that your poll buttons are located at the top of the participant window. You'll see your own name in bold, and then beneath that you'll see a button that has a little A on it, and you can mouse over that to pick your best response for our question here. And I'll have everyone go ahead and answer that one.
And I'm just going to talk to see if this is a better volume, so please let Breen know if this is a better volume or not.
Thanks, Joe, for doing that adjustment. It does sound louder to me, so I think that that should do it. And we've got some comments saying it sounds much better. So thanks, everybody. And we'll go ahead and give everybody just about 5 more seconds to respond to our poll here before we lock this poll and publish our responses to the whiteboard. Thanks for your responses on this one, and we'll go ahead and put those up right now. So I'll pull this down a little bit so we can continue to see our choices and put that there so that Joe, you can discuss. And Joe, don't forget to click on your talk button again to turn on your mic.
It's an interesting distribution of responses. We're actually, the next little section we'll get into this, and you'll see the response that would be the most appropriate. In fact, it is E. I'm sorry, it's E, which is both A and B above. But we'll talk about that in a second. Is my volume still okay? This button tends to move a little bit for some reason. I don't know why.
It's sounding good right now.
Okay. So let's get into what is a disciplinary core idea. As perhaps one of the first important things to think about when you're thinking about a disciplinary core idea is that it's really important in being a key organizer within the discipline. And as such, it has a lot of explanatory power and to explain phenomena. But besides that, and perhaps one of the most important features of what a disciplinary core idea is that it's a tool. If you really have understanding of a disciplinary idea, like matter and its interaction, it can allow you actually to go about and plan an investigation, but also learn more, because it sort of allows you to be able to go and think about how is one idea related to another idea. So for me, this idea of a disciplinary idea, it can explain a lot of phenomena, but it's also a thinking tool. It's actually what structures our ability to take in more information. The fourth idea here, relevant to people's lives, is that there's lots of ideas you can select. So we have to think about what's really interesting to kids and what's going to be beneficial to them in their own personal lives as well as for society. And the last notion related to what's a key disciplinary idea is this notion that it actually develops across the K-12 school year and actually after that, right? So in some respects, once you form these core ideas, you can actually learn and they can develop further as we continue. And that's as we go on and talk about matter and its interactions, you will see how this idea actually does develop across time. Now the value of core ideas is, I mentioned some of these ideas already, but they actually allow you to explore important other ideas and explain phenomena outside in the world. And as such, they really allow you to develop what I like to refer to as integrated understanding. In the next slide, I'll actually show an illustration of what this means. It means that ideas are actually connected together. And it's that connection together that allows us to solve problems and make decisions. Core ideas also allow, if we focus on core ideas in our teaching, they also allow us to make use of the science and engineering practices that Ted pointed out already, and they also reflect the nature of science and scientific knowledge. The other important point behind core ideas is that if we focus on core ideas, they actually allow us in our own instruction to provide a more coherent view of science instruction. Often, some of the literature shows that we often repeat ideas in instruction rather than develop them. And one of the notions behind the framework was actually saying if we could actually focus on core ideas and see how they develop across time, they will present a more coherent vision of what science education is all about. So this is this image about what I mean by integrated understanding. What I'm trying to look, one of my goals in being a teacher and doing the work I do is to support kids in actually building core ideas. And the idea here is that ideas are actually connected to each other. And it's that connection to each other that allows kids to make new connections, but also look at puzzling situations and problems in the world and be able to solve them. So this is where I want to get to, which is having kids have lots of interconnections versus this image over here where you don't see any connections between ideas. So the goal of focusing on core ideas is that as kids go through the grade level, we can get more and more richer ideas like seen in this picture image compared to this image where you don't see any connections. So what are the disciplinary core ideas in physical science? There was 4 of them. You can imagine the challenge that the team had in actually trying to select these because of all the ideas that are out there, what should we focus on? And so we actually ended up with these 4, matter and its interactions, motion and stability, energy, and waves in their application. And as you go on in the series, these will be more focused upon. But tonight, we're focused on matter and its interactions. And it is actually divided up into 4 subsections, you might say: the structure and properties of matter, chemical reactions, and nuclear processes. So I don't know how many of you are familiar with this quote, but you might say, why is the particle nature of matter a big idea, a core idea? Why should we, of all the ideas out there, why should we select matter and its interaction? Well, I'm sure many of you are familiar with Richard Feynman, one of our notable physicists in this era. He passed away now, but he certainly was alive during my time period. And there's this quote that he's a Nobel laureate, by the way. He has this quote that to me is very telling, and it says, if in some cataclysm, some terrible event, all the scientific knowledge would be destroyed, and only one sentence passed on to the next generation of creatures, what statement would contain the most information in the fewest words? And he says, I believe it's the atomic hypothesis, or the atomic fact, or whatever you wish to call it, that all things are made of atoms, little particles that move around in perpetual motion, attracting each other when they are a little distance apart, but repelling each other upon being squeezed together. And so, Feynman, a physicist, took this as being, what would he leave behind? This is what he would leave behind. And so the decision to take matter and its interactions, which at its basis is this notion of the atomic hypothesis that there's these little particles that move around, that can attract each other, repel each other. That's what he picked as the most important core idea. And so I think we have a lot of justification in picking that. If you go on and you ask chemists, and I have a really good friend at the University of Michigan, Brian Capola, and you'll see the references article down there, and you say, what are the 4 questions that chemists always ask? And when they look at something, you always say, what is this stuff? And then they ask, how much of it is there? And where might it have come from, and where might it go? And how fast does it get there? Talking about reaction rates. And how do I know it? How do I know that I have this thing? those 5 questions are, in essence, what matter and interaction gives learners the conceptual tools to respond to. So if over the 12 years of schooling, we can help kids understand what's in that core idea of matter and its interactions, then learners will have the conceptual tools to answer that question, for those 5 questions. As a student of chemistry myself, I was always amazed, and I don't know if you've thought about this a lot, but when you sort of look around, there's lots of stuff out there, right? I mean, there's tons and tons of materials, but there's actually only a few things that make them up. In fact, a majority of material in our world is made of carbon, nitrogen, oxygen, and hydrogen. Yeah, and there's a few other things thrown in there, some iron and some magnesium, but a majority of stuff is literally carbon, nitrogen, hydrogen, and oxygen. And so, you know, how can that possibly be? That's what matter and interaction actually allows kids to answer. How can we account for all the different materials in the world when there are only a few things out, you know, only a few elements out there? So here's a little example, one of my favorite little things. There's some material in the world called malic acid or fumaric acid. It actually it's made up of exactly the same kind of things. It's got each molecule of this substance is actually made up of 4 carbon atoms, 4 hydrogen atoms, and 4 oxygen atoms. There's no difference. And as a result, they actually weigh the same. So they're made up of the same materials, exactly the same amount as the same materials, and yet they have different names. So are they the same or are they different? Do they have different properties? You might want to just take a minute and just think to yourself, is this stuff called malic acid and fumaric acid actually the same, or is it different? You know, how could it possibly be different? It's made up of exactly the same stuff. Well, let's move ahead. And when we look at malic acid, they actually look somewhat the same. They're both white crystals, but they have very different melting points. They melt at, malic acid melts at 130 and 139 degrees, 130 to 139 degrees Celsius. Fumaric acid melts at 287 degrees Celsius. Malic acid is soluble, whereas fumaric acid is somewhat soluble. Perhaps more interesting, malic acid to taste is very pungent. It's very repulsive. On the other hand, fumaric acid has a fruity, acidic taste to it. So they have the exact same formula, made up of the same stuff, they weigh the same. How can it be that they're different? And of course, this is what matter and its interactions allows kids to understand. And if we look more carefully at getting a little bit ahead of what we're going to explore, if we look at the structure and arrangements of these 2 molecules, we see that they actually look different. If you can look at fumaric acid here, you'll notice that these red ones, for those of you who don't know this, these red ones are actually oxygen, and these white ones are hydrogen, and these black ones are carbon. And when you look at this, the fumaric acid, this double bond prevents any kind of rotation. And as a result, you'll see that on fumaric acid, you have an oxygen and a hydrogen at both ends. Whereas in malic acid, again, you have this double bond in the middle that prevents rotation. But now, where this hydrogen and oxygen are located, they're located across from each other. And so this structure, actually what makes these 2 molecules so very different. So understanding how things are put together in their arrangement and other properties of these atoms that we'll get into can actually help kids understand how we can have so many different things in the world. And yet, they're all many, many things are actually made up of these 3 elements. But I was just speaking all of content knowledge right now. And the framework makes this really important statement. It says that science is not just a body of knowledge that reflects current understanding of the world. It is also a set of practices used to establish and extend and refine that knowledge. So in our classes, we shouldn't only be focusing on the content knowledge. In fact, if we want to help kids really learn the content knowledge, we also have to focus on these science and engineering practices that work together with the core ideas to actually build knowledge. And so Ted already mentioned these. I have them here again for you as well. And there's, we might think of these as a more refined set of how to do inquiry. Often I hear the question, is inquiry gone from science education nowadays? And the answer is absolutely not. What we know nowadays is a finer understanding of what we really want to see kids to be doing, and it's this set of science and engineering practices. I always have some fear in putting this list up here because people often think maybe it goes in some kind of pattern, but it doesn't. These things actually work together, and it's working together. You might ask a question that leads you to carry out an investigation, which might help you, might lead you to using computational and mathematical thinking to analyze the data, which might lead to model development, which might lead to an explanation, which might lead to people arguing. So these practices are not linear, and they all work together, but they always work together and with a core idea. You can't separate out the use of a core idea from a practice in building understanding. So if you've often heard me, if you've ever heard me speak in the past, I like using this rope example. We haven't spoken much about cross-cutting concepts today, but cross-cutting concepts are also another key aspect of the framework. And you may have noticed actually that matter is not only a core idea, but along with energy, matter is also a cross-cutting concept, one of the cross-cutting concepts. So, because it's important not only to the physical sciences, it's also important to biology and the biological sciences and the earth and space sciences. But I like to use this analogy of the rope to show that these three ideas, practices, cross-cutting concepts, and core disciplinary ideas, actually work together to form understanding. And when they work together, you actually form richer and stronger understanding. That's why I like the rope idea. The rope idea for me actually shows the strength of understanding that results by working these three things together, these three dimensions together. So understanding content is inextricably linked to engaging in practice, and learning practices are inextricably linked to content. You can't separate them. Content, cross-cutting concepts and core ideas, and practices co-develop to actually build that integrated understanding that we want kids to have in order to solve problems, explain phenomena, and learn more. And when we do this, when we blend these things together, right, we are actually helping kids form a scientific disposition where they're going to be able to question the world that's out there, right? And that's what we want kids to be able to do with their subject matter knowledge. We don't want them just to have these isolated pieces of information. We actually want them to use it. We want them to be able to say, like, you know, what do I need to know more in order to understand it? We want them to ask questions. I wonder if I do something, what's going to happen? And we're going to want them to ask, do I really have enough evidence to build the case that I'm building? So we don't want to make everybody a little scientist. I certainly know that most people won't go into science. I certainly hope as we continue that more of our students will go into science and engineering. But I actually want everybody to have that scientific disposition, to be able to question and say, gee, I wonder if I have enough evidence to support that point of view. What else do I need to know? And then they have those conceptual tools to actually go and learn more. Okay, so with that, part of this seminar series is always to take the stop at a couple of points and say, what questions do we now have? So I wonder, it's time to take a couple of questions about, do you have questions about the definition of a disciplinary core idea? Or questions about the value of core ideas? That's what we're doing now. So hopefully this little section, you get a little bit of an introduction to what core ideas are.
All right, Joe, thank you. And folks, if you'll just type any questions you have into the chat window, I'll filter through there and look for some. Joe, that's an interesting question. Some people question sometimes about whether it makes sense to chunk things together into disciplines, and because there's so much that's interdisciplinary. And I'm wondering, since I'm waiting for any other question, whether you'd like to comment about the choice in the framework and in the standards to put things together as physical science, life science, earth and space science.
I think that's a great question. This understanding of particularly of this core idea that we're looking at right tonight, matter and interaction, is so central to understanding much of what's in biology. So if we're actually going to understand the process of what happens in going from DNA to forming proteins, if you don't understand matter and its interactions, you're lost. If we're going to understand photosynthesis and respiration, you can't understand photosynthesis and respiration without understanding matter and its interactions, or without understanding energy. So to me, particularly today, I think the world is, the scientific world is very interdisciplinary. Much of the research that's happening in the world is happening in interdisciplinary research shops. So I tend to agree with that. But it's hard to change the world all at once. And I hope that if we can have a focus on the core ideas and realize the connections between them, I know the framework tried to show some of those connections. The next generation of science standards tried to show more connections. That if we can help kids to see those connections, we're making a step forward.
Great. Well, we've got a whole slew of questions that have come along here in here. So let me just trying to pull the different ones here. I think Muriel asked the first question here that she feels an expert in biology, but she is struggling with the idea of teaching students when they are not an expert when she herself is not an expert in all areas of NGSS. And I wonder if you've got a sense for that, of how should teachers deal with the issue of them not feeling like they've got expertise in let's say, in the physical sciences, even though they may be expected to teach that.
Yeah, that's another good question. I certainly, I've said this a lot in the past, that the framework in NGSS, the performance expectations, indeed do present challenges to us, right? It's going to actually cause us to go a step further in our own disciplinary understanding. I can tell you right now, as we go in, matter and its interaction has a slightly different look at how kids should think about how matter is held together. And that's very different. It's actually going to cause lots of people, not only people in biology, but people in the physical sciences, to think about how am I going to explain this to students. So it is going to require us to put our professional hats on and actually learn more than we do right now. You may have noticed, for instance, that one of the core ideas in there was waves and how waves are related to various applications in society. And very few of us actually know much about that at all. I totally agree with that. But it's a really important idea. How cell phones work is all about shipping around information on via waves, and so we have to know that. So it will present. I agree with you 100%, and it is going to cause. It is going to allow. And we are going to have to sit down and open up our books. Hopefully, there'll be a number of professional development sessions that will allow us to further study and learn together. So I agree with you.
Okay. One other piece here we haven't quite got to, but I think this is going to be a quick, easy question. When I am lesson planning, is it better to view the performance expectation standards as they're organized by DCIs, or should I look at the performance expectations arranged by topic? I think the answer is it doesn't really matter.
Well, yeah, it could be. What I was going to say is in Michigan, we're actually looking at them by topic and not by DCI. But, you know, it depends on how to do it. But what's more important, I'm going to go back to what Ted said this isn't the focus of today, but I'm just going to stress it again. What we want to realize is that performance expectations are what kids will be assessed on, and they are not our objectives for our lessons. The goal that we're going to have as teachers is to think about how do we plan an instruction to help kids get to that point, right? So they are not lesson plan objectives, they're not unit objectives, they're what kids are going to be assessed on, and what we have to do as teachers is break down our instructions to say, how am I going to get kids there?
Great. Well, we've got lots of other questions to do here, but why don't we move along, and then we'll hopefully have more time for some questions towards the end.
Right. So now that
cover some of these issues.
Right. So now that everybody has this little bit of a pattern about what we're doing, if you can now just type in some questions into the chat window, and then Ted will be ready when we do this next little question part. Okay. So the first idea under matter and its interaction is the notion of structures and properties of matter. And of course, what this core idea does, or sub-core idea, what it works on, is helping people understand how do particles combine to form a variety of substances that one observes. This isn't getting to how they combined. And so what's important here is that the substructure of atoms determines how they combine and rearrange to form new substances. And what's important here is for having kids understand the electrical attractions and repulsions that happen between charged particles in matter that allows us to understand the structure of atoms and the forces between the atoms that cause them to form molecules that can range from, you know, two or three atoms like water or hydrogen or oxygen to thousands of atoms like in proteins. It's actually understanding those forces. So atoms actually combine due to these forces. Atoms also combine due to these forces to form extended structures like what we see in metals or what we see in crystalline solids like substances like sodium chloride or many of the other ionic compounds that we'll see. And these two bullets, by the way, this bullet and this bullet, are perhaps two of the very subtle but very important differences that you'll see in matter and its interactions. There is no mention of the word covalent bonding. There is no mention of the word ionic bonding. Rather, is a stress on helping kids understand that why atoms come together is a result of these forces, these electrical attractions and repulsions. This is a very different approach to understanding bonding. It's not the typical approach that if you crack open in many textbooks. But it's an important one because many of our students right now can memorize ideas that, oh, covalent bond is a sharing of electrons. But they don't understand what we mean by that it means that it's actually an electrical attraction. And so the framework is actually pushing us to go this level deeper. That's why this is a core idea, because it's presenting this structure to understand why do some things come together. Similarly, these electrical attractions also allow us to understand within and between the arrangement, the very property. It can also help us understand the various properties of materials. So why do molecules, when they form these various substances, why is that? So and these also are explained by electrical forces between the molecules. So why does water, for instance, have such a high boiling point, whereas something like carbon dioxide has a very low boiling point? How can we actually understand that? We have this phenomena. Water boils at 100 degrees Celsius. Carbon dioxide, which is a heavier molecule, so you would think based upon mass, would actually boil much higher. It actually boils at a really low. Why is that? And it's because of the electrical forces between the molecules. So the other important part here is part of the atomic hypothesis that Feynman mentioned, that within matter, atoms and their constituents are always in constant motion, and the arrangement and motion of atoms vary in characteristic ways, depending on the substance and its current state. And that really depends upon the temperature and the chemical composition. So understanding how molecules are put together and their arrangement and the temperature will really tell us a lot about how different types of substances will behave. So one of the questions we might want to ask for our own teaching related to PS1A is what science practices work well with this core idea? What science practices work well with structure and properties of matter? And all of them actually can work, but I've actually picked out 3 that I think are really important. And that's developing and using models, planning and carrying out investigations, and constructing explanations. One of the things you might want to notice here is how active these 3, actually all the practices are. So you can use all the practices. Asking questions for it also is very important. They're all very active. It's kids developing models, kids planning and carrying out investigations, kids constructing explanations. And it's when the kids actually can do this, if a kid can actually develop a model. So if I can ask a student to say, I want you to develop a model of what happens when something boils. What's going on when something boils? What happens? Give me a model for when something melts. And if a kid can develop a model and explain that to me, and as they get older, actually add more parts to it, then they have an understanding that they can apply to explain other phenomena in the world. That's the importance of these scientific practices. If they can construct a model, give me an explanation, that's what allows them to actually form that integrated understanding. So here's an example. This is actually from a middle school curriculum. And what you see in front of you is sort of a pre-test that we gave the students. And this is actually, this is from a 6th grade classroom actually. So it's important to know that this is 6th grade. And the example says here that Shannon had a small bottle of bromine. We wanted to use bromine because we wanted the gas to have a color to it. The bottle was closed with a cork. She tied a string to the cork and then placed the bottle inside a larger bottle, as you can sort of see over to the right over here. And she sealed the larger bottle shut. Well, you can see it shut over here. And next, Shannon opened the smaller bottle by pulling the string connected to the cork. And figure 2 shows what happens after the cork of the small bottle was opened. And so you'll see what's happening over here. And the question that for the student is, first draw a model that shows what is happening in this experiment. And then a second, explain in writing what is happening in your model. It's what we see here is simply a descriptive idea just looking at the pictures, right? And what should be expected, this is a 6th grade student, and they just began their school year. So we just see this sort of these arrows coming out. This is a very descriptive, continuous model. It's very characteristic of what we see many students doing in middle school. Some kids continue to do this in high school. Some kids actually continue to do this in college and beyond. They often give these very descriptive models. After going through some very careful instruction over a long period of time, an 8 to 10 week unit in which kids were actually building models and arguing models and experiencing different phenomena, students took a post-test, and we see a very different look at what's happening. And so in this case, you'll see the key over at the side. You see air molecules, you see bromine molecules, and you see that the arrows indicate movement. And the description is, in my model, the small bottle has just been opened, and the bromine gas is moving out of the small bottle and into the big bottle. Each molecule is moving into a straight line until they bumped into something, change directions, and continue in another straight line. The bromine gas is filling the whole big jar. Now, if I can get students in the 6th grade after an 8 to 10 week lesson unit to actually get this far in understanding the particle model, we've really made some nice progress. As you can see, here's one of our bromine molecules, and it's moving in a straight line. Here's another bromine molecule. It hits the side of the container and it bounces off. Here's an air molecule, and it hits the side of the container. It moves along, it hits a bromine molecule, and it bounces into a container. So the student has a pretty good understanding that gases are in movement and that gases are made of tiny little particles. This student at this point does not know yet about any subparts. She doesn't know that bromine is actually made up of 2 things. She doesn't know that oxygen is made up of 2 oxygen atoms. But she does have a good understanding, or he or she has a good understanding of the particle model. And that's the value of blending practices with the core ideas. Here's another example. This is now a 9th grade physical science class, a little bit jumping up. This is trying to help kids understand what the structure of an atom looks like, right? So now we're peering inside the atom, and it's really important that in the framework, having kids understand the notion of electrons and protons and a nucleus doesn't happen until the high school. And in this case, the kids actually were trying to understand they learned about charges, so they know that the world is made up of negative and positive charges, or at least things that attract and repel each other. And then their experience of simulation, actually this is the Rutherford experiment where he actually shot some alpha particles in and observed what happened to the alpha particles. And then as a result of watching that simulation and actually collecting data, they were then asked to draw a model of what might possibly explain this. And so what we see here is a student actually drew the electrons on the outside and having the protons on the inside. So with that, we're going to take another poll and move on to another part of tonight's session. And this poll is now about how do you help kids develop core ideas. And so it says core ideas should be developed over time as students grapple with more complex situations. Most core ideas can be developed, taught in a single class period, and teachers should focus on core ideas in teaching science, but not for assessment. So pick your answer.
Thanks, Joe, and I'll just jump in and remind everyone about those poll buttons, that they're located at the top of your participants window right beneath your own name. And if you weren't able to respond to our poll before or weren't here with us, that's where you can find it now. And I see that most folks have already responded. We'll give everyone just another couple of seconds to submit their best answer. And I'll go ahead and lock our poll now so we can take a look at what everyone thought. And I will turn it back over to you, Joe, to discuss the results.
Well, I'm glad to see that everybody, that no one picked B. I'm very happy with that, that we can't teach a core idea in a single class period. And that a lot of people picked A, actually, that this is an idea that has to be developed across time. And that's a very excellent way of thinking about it, because core ideas, as I said before, are actually forming these conceptual frameworks or structures that allow kids to think. So I'm very pleased with that. And we're going to go on a little bit further and examine that idea of development across time just a little bit more in depth, and then relate it to properties of matter. So core ideas indeed do develop over time. And actually, anytime we try to learn anything difficult, it always takes time to come together as we actually grapple with ideas. And sorry, my phone rang, so I got distracted. Hold on, I'll start over again. So anytime learning difficult ideas takes time, as we often grapple with them and work with other students to help us synthesize those ideas. And so this, the idea of development across time isn't anything new. It's actually just the idea that you got to build on prior knowledge. But often we don't do that in our teaching. I'm a teacher myself, and I know it's really hard to take ideas day in and day out and help kids actually build on those ideas one day after another. But that's how understanding is actually built. If we can facilitate new understanding, building on existing understanding, that's how a core idea should actually be developed. But it's very dependent upon instruction. It's really going to depend upon what we do. And so the framework and the next generation science standards is saying, the people in K5 and K2 and then 3-5 really have to lay a foundation for each other. Matter and its interactions are very important at that level. And then at middle school, we have to take it a step further. And then at the high school, we have to take it a step further. And if any one of us breaks down, then the kids aren't really going to have that time to really grapple with these ideas. So here is an example using structure and properties of matter. So by the end of second grade, we want to assume that kids develop a macroscopic model of matter. It's very descriptive, but they know something. They know that some things are solid, some materials are solid, some materials are soft, some materials will melt, and they'll go from a solid and become to a liquid. Some things don't do that. They burn. So this is a very macroscopic model of matter, but kids have had experience with this, and they can be able to say this thing. Some things I can take a solid, I can make them a liquid. From that liquid thing, I can make them a solid again. So that's a macroscopic model. As they move to the 5th and 6th grade, they're starting to develop that particle model, which can help them explain phase changes in phases. So why is it that something can go from a solid to a liquid? Why is it that a gas can travel across the room? They're developing this particle model. They don't have a finer structure yet of what these particles are actually made of, but they know that matter is particulate and that it can explain some phenomena, right? The important aspect here is that these models are explaining phenomena. As they move to the 8th grade, then we see students starting to develop an atomic molecular model. So they realize that, okay, these particles are actually made up of molecules. Molecules are actually made up of atoms that join together. They don't know why the things join together, but they know that water is always, I'm not saying I want kids to memorize this, but they know that water is always H2O. They know that oxygen is O2. They know that a sugar, is C6H12O6. It has a certain set atomic structure, and that's what identifies it and gives it its properties. They can use those ideas to explain chemical reactions. So they now realize that in chemical reactions, the starting materials rearrange to form new things, and those new things have new properties. And so they can identify these things, these new materials, based on their new properties, but they explain it by these atoms and molecules rearranging to form new molecules that have a different composition. When they get to high school, this is where they now begin to get a more of a mechanistic model that actually allows them to explain why these things occur. This is where they're learning about electrical attractions and repulsions, electrical forces, and how those electrical forces actually explain why certain atoms will come together and why certain molecules actually stick together as well. So, as I said before, one of the things we have, developing core ideas is really, over time, is really dependent upon instruction. And what we do in our class really makes a big difference. And I just listed a couple of strategies that you might want to try in your classroom. I know it's, to me, it's always difficult to do some of these things, right? But we always want to activate students' prior knowledge and users' experiences. So asking kids various questions related to how is what we're doing today related to what you learned yesterday. Make explicit links to what happened before. So if you actually did a unit on the particle nature of matter, where you help kids understand ideas about solids can go into liquids and liquids go into gases, then when you go into a unit on perhaps in the earth sciences where you're talking about the water cycle, you can relate that back to phase changes. Make explicit how core ideas explain phenomena and can solve problems. So you really want to point that out and get kids to say, how are we using our core ideas? And we want to make sure we use these links, use and link core ideas to explain the phenomena and solve problems. So it's not only making them explicit, but making sure we point out the links. Okay, so with that, we're going to now take some questions on the structure and properties of matter, or questions about ideas developing across time.
Great, Joe. I've got some that we've saved up over the time here. One question that came up earlier was, how did the writing teams of either the framework or the standards, how did they go about deciding what was age appropriate?
It's a good question. We certainly dove into the literature, right? So each team was made up of a variety of different people. We had people who were, it wasn't big groups, but it did have, like it had some classroom teachers in it. It had experts on student learning in that area. It had people who, at the college level, who also worked in K-12 world. And so we had different kind of expertise, and we dug into the literature. Now, not everything is there, so we had to make some guesses, right? There's a lot of work left in the world, for those of you who want to go on and study science education more. There's a lot of work left, right? Especially developing, how do we really help kids develop ideas across time? We made some of our big hunches, we made some guesses, but there were some holes there. The notion that kids have this continuous model that I showed you before, and that it's hard to get rid of that continuous model and move to a particle model, that is well known, right? If you ask your kids, and I would challenge my high school teachers out there this year as you move forward in teaching high school chemistry. Ask your kids what exists between one particle in the air and another particle in the air. And my guesses are going to tell you there's another particle. It's really hard for kids to get this idea that in gaseous molecules, there's actually nothing in between some molecules. Everybody has a hard time understanding that. And usually when you ask them what exists between this particle and that particle, they'll say another particle. And you'll say, okay, good. What exists between that particle and that particle? They'll say another particle. And what you really build up with, so even though they might have a particle model, you end up with a continuous model because they keep saying there's another particle. So we really, we dug into the literature because there is some really known stuff, but there's also areas that's really unknown. Some, in fact, in matter and its interactions, we're a little bit luckier that area is much better studied, for instance, than waves and their applications.
Sorry, I forgot to hit the talk button. So that this ties into some other pieces here. A couple different folks had raised of why is there no discussion of electrons and atomic nuclei prior to 8th grade if it's so important? Or how do I help my middle schoolers understand to develop models of simple molecules without valence electrons, or other aspects that don't appear in the standards till high school? Do you want to give a little feedback on that?
Sure. A lot of the literature really shows that that's too advanced for many kids to understand. And what we don't have them really understanding is what's an electrical attraction. So in middle school, you really want to start helping kids understand electrical interactions and not talk about electrons yet. That question that that how we explain how some things are how you get negative and positive will be related in high school. But at the middle school level, you really want to get them to understand that you can charge things and that those charged particles can either be repulsive or attractive. And it's building those understandings that are really important. In the past, we literally just told our kids they're valence electrons. Well, what's a valence electron? What does it do? And so it's helping kids understand more fundamentally what electrons do is what's really critical. And it's building those ideas. You will notice, and I haven't talked about this yet, the framework actually talks about fields. And there's been a lot of questions related to, really, I have to help my kids understand fields? Well, if we can help our kids understand electrical fields, we're really going to move them a lot forward to understand about why things bond together the way they bond together. And so that's why there's this emptiness, there's no focus on valence electrons because we're trying to build the understanding that will be stronger in helping them understand electrical attractions. When they get to high school, electrons and proteins are there, and it's very important to understand why things come together. But in middle school, it's far too early, and it's certainly way too early in elementary school. When you just have kids do that, all they're doing is memorizing terms. Yeah, they can memorize the terms, but they really don't understand what it's doing. That's very clearly what the literature shows.
Great. Sheila here had asked, do you have recommendations on the order of teaching the concepts at the middle level? Or that could also apply to high school as well, since all the standards are just grouped together in middle school and or high school.
And I guess I'd ask, just in physical science or all areas?
It doesn't specify here. You could do it either way. I'm assuming a reference to the appendix on the model course maps would be helpful.
Yeah, it's a great question. For me, I think to understand a lot of what happens in biology, there's some areas in biology you can deal nicely, all the descriptive areas, right? It's great. But when you start talking about photosynthesis and respiration that we often do, having kids understand concepts of energy, having kids understand the nature of a chemical reaction becomes very important. So to me, actually helping learners understand ideas related to energy and helping learners understand ideas related to chemical reactions are really critical. So I would always focus on those first because those are really critical to understanding various other ideas. How do you understand plate tectonics, for instance, if you don't have a sense of energy? How do you understand rock cycles, how materials cycle in the environment, unless you understand the nature of chemical reactions and the properties and structures of matter? So at least that's my cut on it, right? I was so heavily involved in trying to finish off the standards that I didn't really think of what would be the sequence. So right now that is what I would say, because to me those are really important ideas that drive our understanding of the other areas. Now, you could look at it the other way. You could, for instance, if you're studying ideas within ecosystems, it gives you a wonderful opportunity to bring in ideas about energy, right? So it could give you a context for, you could develop some wonderful units that actually serve as the context to understanding other ideas. Going back to that question that we said earlier about interdisciplinarity.
Great. Just one last question. We'll go and move on. Rachel here asks, do you have any suggestions on how to make the disciplinary core ideas less frightening for elementary teachers who are not experts in this science discipline?
Great question. To make them less frightening is to realize that what you're trying to do is understand the world out there. And in the elementary level, just remember that the model, what you're seeing when you read the framework, for the most part, is where we want to get kids to by the end of 12th grade. And I would really encourage you to read what kids should know about that disciplinary core idea by the end of 2nd grade and by the end of 5th grade. That'll make you less afraid if you focus on that. Just like if you go back on my slides here, if we go back here, by the end of second grade, we want kids to understand this macroscopic model, right? Just to have kids understand that things can exist in 3 states, solids, liquids, and gases. And that sometimes you can get them to go the other way. You can get things to go back from a liquid, go back from a gas to a liquid to a solid. Sometimes, so that, hopefully that's not too scary. And by 6th grade here, it's starting to get a little bit, maybe if you didn't have any experiences in science, understanding a particle model and certainly helping kids develop a particle model can start to be a little bit more frightening. But again, that's what explains a lot of those macroscopic phenomena that we actually observe. So I would, to me, the insight is really looking at what is expected of you at the end of 2nd grade and at the end of 5th grade to sort of, or end of 5th grade to sort of, relieve that, gee, I really don't have to explain the structure of atoms.
All right, go on. Let's go on and look at some more questions a little bit.
Okay, so we're going to do one more poll here. And why are chemical reactions important? It says chemical reactions occur all around us. Why are chemical reactions important? A, they occur all around us. B, chemical processes underlie many important biological and geological phenomena. Chemical reactions account for the conservation of mass. All the above.
Great, thanks, Joe, and we'll give everybody just a moment or two to respond to this one. We've got most folks are jumping in on this one really quickly and have their answers already submitted. So we'll go ahead and give just about 5 more seconds before we lock our poll and put up our responses to the whiteboard. And here we go. I'll turn it back over to you, Joe.
So in this case, indeed, D is the appropriate answer, right? Chemical reactions are occurring all around us, right? They're occurring within us, outside, they're occurring all the time. They're certainly important to biological phenomena and geological phenomena. And mass is always conserved in a chemical reaction. It's never destroyed. So indeed, it is D, and those are some of the underlying features that when you read the core idea in the framework that you'll see. So just to do another fun little thing here, burning is a very common phenomenon, right? We see it all the time. Things burn down, forest fires, etc. And you can actually burn steel wool. If you make steel into these really fine things, I think many of you have seen steel wool, you can actually burn it. So I'm going to ask you a couple of questions about what happens if we burnt it. So initially I took the mass of the steel wool and it was 5.72. And then I'm going to light it and it's burning. So you can see it burning in the dish here. And I want you to make a prediction. We're not going to have a poll on this, so I'm just going to ask you to think to yourself, what would the mass be? Is the mass going to go down? Is the mass going to go up? Is the mass going to remain the same? And I'd like you to think a little bit to yourself, why am I giving that answer? Why am I saying it's either going to go up, go down, or stay the same? So if we let it burn for a while and then we go and we look, we notice that the final mass of the steel wool is 6.56. It actually went up. So I don't know how that compared to your particular response, but what might explain this? Most students actually, most people, I do this a lot whenever I can light something and have a scale around, will predict that the mass is going to decrease. And that's because actually when we take a log and we burn a log and then we mass the ash that is left over, it actually goes down. And that's because we're sort of in an open system. We're not in a closed system. In this case, it's slightly different. When you burn a log, you have a lot of carbon dioxide escaping into the environment. And so the ashes that's left over is much lighter than the log. But in this case, in burning the steel wool, you also need oxygen. Any burning reaction actually involves oxygen. And in this case, the steel wool is also reacting with oxygen. We can see again, we can see the flame here. You can see it's all burning. And of course, it had to be reacting with oxygen. You're forming iron oxide. But in this case, the iron oxide actually isn't forming carbon dioxide and going into the atmosphere. It actually stays in the dish. So in this case, you're taking iron plus oxygen, and you're forming another solid called iron oxide. And so you see the solid, the mass of the material actually going up. There wasn't a gain of mass. The mass that's there is actually a result of the oxygen that came from the air. So mass is indeed still conserved in this case. And this is what PS1B is all about. It's all about chemical reactions. How do substances combine or change to make new substances? And how does one characterize and explain reactions and make predictions about them? These are the two main questions that PS1B attempts to answer. And what we see here is that some of the major ideas here is that many substances react chemically with other substances to form new substances with different properties. That's the essence of what chemical reactions are all about. And of course, that happens because the atoms that actually make up those original materials are simply rearranging. When you burn a log, you're taking a carbon, hydrogen, oxygen substance. You're reacting with oxygen. And all that happens is when you burn, is you're rearranging everything to form carbon dioxide and water molecules. In the case of the burning of the iron, you're starting out with Fe, and you're starting with oxygen, and you're going to form a compound that's a mixture of, that's a chemical compound of iron and oxygen, Fe2O3. So you're forming iron oxide. So the total number of atoms is always conserved. You don't create or destroy atoms in any chemical reaction. So looking again at sort of a progression of these ideas across time and going back to that question about, what can I do to feel more comfortable at the elementary level? Again, it's really important to have kids have experiences with materials. But at this level, again, we want them to get a descriptive model. We want them to know that heating and cooling a substance may cause a change. Sometimes that change is permanent. So if I take some sugar and I heat sugar, you can make candy in your classroom, for instance. It changes, and that change is hard to bring back. On the other hand, I can take some other stuff, like water, or like an ice cube, for instance, and I can heat the ice cube. That ice cube will form a liquid, but I can get the ice cube back again if I put it in the refrigerator. So that's a descriptive model. The kids don't know why what's going on. They know, making a link over to energy, that I have to make something hotter or colder, but it's a descriptive model. At the 5th to 6th grade level, they still have a descriptive model, but they know that when two or more substances, sometimes maybe one substance, in this case it's mixed together, I may form a new substance with different properties, may form. Not necessarily all the time. Sometimes when I mix things together, nothing happens. But then I don't have new properties. The thing that results, I can separate out those parts and they have the same properties. When I take two or more substances and I mix them together and I get a new thing, I have actually new properties. But mass is always conserved. At the 8th grade level, it gets a little bit more sophisticated. It's here where where students need to understand that it's the atoms that rearrange into molecules, that they regroup. And they may regroup to form different structures, right? So it's not like you're changing the number of atoms in the substance. It's the same number of atoms, same type of atoms like we saw in the beginning, but they have a new structure. And when you do that, you get a new substance and you have new properties. And once again, atoms are always conserved. Again, it gets a little bit more, here students also begin to realize that some chemical reactions actually release lots of energy. In other cases, it doesn't. So burning is actually an example of a chemical reaction, which typically releases lots of energy. At the 12th grade level, we see kids understanding more about chemical processes, their rates, and whether or not energy is stored or released in a chemical reaction, and the importance of understanding collision theory, and again, once again, this rearranging of atoms into new molecules. We also get into the notion of equilibrium, that there's a dynamic and reversible reactions determines the number and types of all molecules in a substance. You know, I haven't talked much about this, and I know you're going to have a session on energy soon in the future, but one of the fundamental misunderstandings that many people have is that often in a chemical reaction, when you break the bonds, energy is released. That is actually a misunderstanding of what happens. In fact, to break the bonds, to break any chemical bond, always takes energy. It's in the formation of the bond that energy is always released. And hopefully when you do the energy unit, Jeff, that's a hint for you. When you do the energy unit, you're going to study that notion about in a chemical reaction, to break bonds, it takes energy. It's in the formation of new bonds that energy is actually released. So again, going back to this question, what works well? Developing and using models, of course, constructing explanations, or planning and carrying out investigations. And I have another example for you. In this case, is once again a middle school example. And this is no, I picked the wrong one. Sorry, this is not chemical reactions. Sorry, I grabbed the wrong slide. I apologize. So here you go, but I'll do this anyway. This is more related to properties. This is, you've got four liquids, and you're asking the kid, is there a difference between them? And you see the example below that liquids 1 and we were asking the kids to write an explanation, and it says liquids 1 and 4 are indeed the same substances. And it says, looking at the data, the properties including density, color, and melting point are the same in liquids 1 and 4, but mass is not a property. Density, color, and melting point are all the same for liquids 1 and 4. Since all these properties are the same, 1 and 4 are the same substances. I'm sorry, I thought I had one on chemical reactions. I grabbed an inappropriate slide. So it relates back to the first one. So questions regarding PS1B, questions about how this core idea develops over time, questions about the use of practices.
So Joe, we're running a little bit behind schedule here, so we're going to skip this question section and go on to towards the end here. So the last sub-core idea is actually related to nuclear processes, and here this is also a very important part of what happens to get new stuff. This idea really isn't touched upon until high school. But the notion is what forces hold the nuclei together and mediate nuclear processes. And so why doesn't the nucleus fly apart? You know, when I was a kid, I tell you, I struggled with this all the time. I kept saying, everybody's teaching me that when I bring negative to negative together, they repel each other. When I put positive to positive together, they fly apart. So why in the heck in the nucleus can I have all these positive things crammed together? It always bugged me. I have to tell you, you know, and I always have to, what's going on here? And so nuclear processes are really important. They're not covered until into high school, because in order to understand them, you really have to understand the parts of the atom, and you don't get to the parts of the atom until high school. So just some quick conclusions here. Core ideas explain a variety of phenomena, allowing us to solve problems and learn more. Matter and its explanations explains how we have such a diversity of material in the world with so few atoms, and how we can identify them. And so, as such, matter interaction is not only critical to the physical sciences, it's actually really critical to the biological sciences and the earth sciences to explain many of the phenomena in those disciplines. And of course, just going back to this beginning slide, it allows us, matter and its interactions, allow us to actually understand these 5 questions. What is this stuff? How much of it is there? Where might it come from? How fast did I get it there?
going to the kinetics thing in high school, and how do I know it, getting to the properties. Ted mentioned this before to you guys. If you haven't read the framework, I'm going to encourage you to download it. You just can take your smartphone, hang it over this little image, and you'll get a free, thing will get downloaded right away. And now we're back to questions to end this session.
Yeah, Joe, so what we're going to do is I'm going to share a little bit of information about resources NSTA has. We'll have participants go through and fill out their surveys, and we'll stay and answer some questions after that piece comes together. So just to give folks some information here, Joe's got some other pieces here. You can look those up if you want to look at the slide set. And there's also information about how you can contact Joe, so in place here. I really want to thank him for all he's done here tonight. But I also want to point out, we've talked about before, the websites for the Next Gen Science Standards mentioned here, nextgenscience.org, are also our site. We've just actually, in the last week, revamped that. It's a first preview, really, of a whole new website for NSTA, so you may want to take a look at that at some point. We have a listserv for our members and discussion forums in the Learning Center that anyone can join and look into, which can continue the conversations. Both have areas specifically just to discuss NGSS, which we would encourage you to. As has been mentioned, we've got some other pieces on the core ideas coming up. I want to note that we've had a little bit of change in our schedule for those of you who may have signed up earlier, that 2 weeks from today we're going to work on waves and their applications, and we've shifted that, and then not until second half of October will we do motion stability forces and their interactions. Energy will be on October 8th, and then we'll move into the earth sciences. And next, for those of you who are life scientists in the room or interested in engineering design, that'll come up after the first of the year. An online short course that we're doing that I really encourage you to check out if you're interested in engineering, visualizing K6 engineering education, and the information you can find there. We have, for those of you who didn't see, and I noticed a number of people hadn't seen our previous web seminars, I'd strongly encourage you to take a look at our previous ones. Joe did one for us last year on one of the practices. We also have articles around NGSS in all of our journals. The NSTA bookstore has a number of books. We've mentioned the framework a couple times. You could actually get the standards in print as well, and NSTA has developed reader's guides for both books as well. Coming very soon, Roger Bybee, who's one of the writing team leaders, did a book on translating NGSS for classroom instruction. That'll be coming out, I think, in another month or so. And finally, conferences for this fall in Portland, Oregon, in late October, and then Charlotte, North Carolina, and Denver. And I hope to see a number of you people at our national conference in Boston next spring. With that, again, thanks so much to Joe, who has really been a tremendous value throughout this process and very helpful. Give him a round of applause and pass things off to Bryn.
Thanks a lot, Ted, and I also want to echo your appreciation for Joe Krajcik for presenting tonight's web seminar. Fantastic content tonight, Joe, and thank you everyone for contributing to our discussion in the chat window as well. And thank you for giving your round of applause on our participant window. Big thank you to Ted Willard as well for sharing information about NGSS. We would like to thank the sponsor of today's web seminar, the Carnegie Corporation of New York. And a thank you to our administration of NSTA for their support for web seminars. And just a reminder about our upcoming web seminar calendar. You can join us for tomorrow's presentation on the engineering design process on the moon, and then come back next week to learn about applying for the NSTA Board and Council, and on the 18th, analyzing solar energy graphs. And these programs and more are available by going to learningcenter.nsta.org/webseminars. Thank you everyone again for your participation today, and we look forward to seeing you again soon.